All right, good morning, everyone. I'd like to thank the organizers for the invitation to speak in this symposium, which already looks to be a great day of cross-fertilization and discussion. And as Kobe mentioned, what I'll talk about is geologic time, or more precisely, the geologic time scale, both in terms of absolute age, that's where I'll start my talk, and in terms of the events that have shaped the geologic record and which provide a relative timing of key events in Earth history. So to begin, we need to get a basic understanding of rocks, which are the geologist's tools to study the Earth, and they're also an archive of information on the processes and events that have occurred over Earth history. And so we divide rocks into three categories: igneous rocks, and these metamorphic rocks, and sedimentary rocks. The igneous rocks form when magma cools and crystallizes into, forms a matrix of crystals, and the magma itself is a melting product of pre-existing rocky material. We have sedimentary rocks when either igneous or metamorphic rocks are exposed to surface conditions, they weather and erode, and the particles and solutes end up being deposited in sedimentary rocks. And we have metamorphic rocks. So when either igneous rocks or sedimentary rocks are buried to great depth and exposed to high temperature and pressure, the mineral assemblage in them changes to reflect the stability under high pressure and temperature, and they become metamorphosed. And again, when either metamorphic rocks or sedimentary rocks are buried deeply enough and heated enough, they may partially melt to give us back igneous rocks. And so this is what we call the rock cycle. Now, humanity has wondered from very early on about the age of the Earth. And according, so let's have a look at some of the estimates, right? According to the Bible, the Earth is 5,000, almost 5,800 years old. And the exact number depends on how one does the accounting. This is the Jewish, the year according to the Jewish calendar, which is said to have started when the world was created. But in the 17th century, Archbishop James Ussher made an independent estimate and came up with an age that is about 250 years older. But whichever age of creation is suggested by the Bible, geologists have argued for a long time, and I hope this is visible in the back. Geologists have argued for a long time that the Earth was actually much, much older. And they base their arguments on observations of repeating sequences of sedimentary rocks, like the ones that are shown here and folded here. And each of these layers they understood to have formed by processes that they knew to be long, lasting perhaps thousands or tens of thousands of years. And so many, many repetitions of these layers meant that the Earth was in fact much, much older than the Bible suggested. In fact, many geologists thought that the age of the Earth was infinite, that it had been around forever. There were some who tried to come up with more quantitative estimates of the age of the Earth. For example, in the early 18th century, Edmund Halley came up with the idea that we can use the salinity of the ocean to measure how long the ocean has existed if we knew the fluxes of material coming into the ocean because of precipitation and runoff and in groundwater as well. So we have evaporation out of the ocean. This rains on land, dissolves material, carries it into the ocean, and that accumulates as salt in the ocean. And so if we know the mass of the ocean, the salinity in the ocean, and the fluxes of solutes into the ocean, we can calculate how long it should have taken for the ocean to become this salty. And one immediate thing that comes out of this is that the Earth is not, the age of the Earth is not infinite. Otherwise, the ocean would be saturated with sodium chloride, much like the Dead Sea. Halley didn't try to perform this calculation because he knew that he didn't have good enough constraints on fluxes coming in rivers. But almost 200 years later, John Joly did the calculation with some early estimates of riverine fluxes into the ocean and came up with an age of about 100 million years. We have now much better constraints on riverine fluxes, but more importantly, what they didn't know of was that there are processes that remove salt from the ocean. So salt doesn't just make it into the ocean, just sit there until the ocean becomes saturated. There are many processes that actually remove salt from the ocean or remove solutes from the ocean, even when the water is undersaturated. And so this is a gross underestimate of the age of the oceans and the age of the Earth. So physicists of the time, and especially William Thomson, which was later knighted and given the title Lord Kelvin, and after whom the scale was later named, he realized that an infinite age of the Earth violated the laws of thermodynamics, as, that Avishay mentioned a few minutes ago. And he calculated the time it would take a molten sphere of rock, starting at a temperature of 1,700 kelvins, to cool down so that so that the ultimate heat flux resembled the modern heat flux, which again there weren't good measurements of the heat flux when he first made this suggestion. But when some measurements were made of the heat flux, of the geothermal gradient, the change in temperature with depth into the Earth, he performed this calculation and came up, and I should note that the assumption was that the Earth cooled only by conduction of heat. And so he was able to calculate that the age of the Earth was, again, about 100 million years. But what Lord Kelvin did not factor into his calculations was that the Earth cooled much more effectively than just by conduction. And this is because of convection in the mantle. The mantle is a viscous fluid. It's not liquid, it's solid, but on geologic timescales, it's viscous enough that it flows. And what happens is basically that there's heating at the core mantle boundary, and the warm material rises up towards the surface and is replaced by cooler material that comes down from the surface. And this is a much more efficient cooling mechanism than just conduction of heat. And so in order to end up with the geothermal gradient that we have today, there's a lot more heat to mine from the interior of the Earth. And so this again gives an underestimate of the age of the Earth. A former assistant of Lord Kelvin's, John Perry, suspected something like this. He's quoted as saying that it's hopeless to expect that Lord Kelvin made an error in calculation. Instead, he focused on Lord Kelvin's assumptions. The assumption was, the main assumption being that there was no additional source of heat inside the Earth, and that the Earth cooled only by conduction. So he did not know, just like Lord Kelvin, he didn't know about convection in Earth's interior, but he carried out the same calculation under an assumption of high interior, what he referred to as quasi-conductivity. And this had essentially the same effect as our understanding today, that there is in fact convection. And the result was that his estimates for the age of the Earth were about an order of magnitude larger than Lord Kelvin's, actually 1 to 2 billion years. And this really, the range here depends on how thick one assumes the conducting layer to be at the Earth's surface, right? Because the Earth is not convecting all the way to the surface, right? There is a thin conducting layer at the top. Also missing from Kelvin's calculation, but also from Perry's calculation, simply because it had not yet been discovered, was radioactive heat. So they assumed that the only source of heat was this initial molten sphere at an initial temperature. They did not know that there is actually additional heat generation by radioactive decay of unstable elements. This lengthens the age by a bit, but not much. The main difference going from Lord Kelvin's calculation to John Perry's calculation is actually the inclusion of convection or a quasi-conduction that John Perry included in his calculations.
Beyond the astronomical rotation?
1 billion is 10 to the 9 years. Yes, it's 1,000 million years. All right, so the entire story and all its intrigue and scientific politics is wonderfully laid out in an article by England et al. Came out in the GSA Today in 2007, if anyone's interested. So the debate was finally settled when Marie and Pierre Curie discovered radioactivity. So what they basically discovered and were jointly awarded the Nobel Prize in 1903 was that the isotopes of some elements were unstable and that they decayed with half-lives that varied over many, many orders of magnitude, from seconds to billions of years. Parent isotopes decay through a series of alpha and beta decays into ultimately decay to stable daughter isotopes. And here we have two examples of decay of uranium-238 with a half-life of about 4.5 billion years, and uranium-235 with a half-life of 0.7 billion years. And they decay through this complex series of unstable isotopes all the way down to stable isotopes, mostly to isotopes of lead. Uranium-235 mostly ends up as lead-207. Uranium-238 mostly ends up as lead-206. So in the early 20th century, Ernest Rutherford, a physicist, realized that this could serve as a chronometer or a clock for geologic materials. And he suggested using the decay of uranium-238 and 235 to lead-206 and 207 respectively as a means of measuring time since a mineral formed. So how does this work? Say we have a mineral that has no lead in it initially, but some uranium, and zirconium silicate is a good example. It contains no lead at the beginning. It's an igneous mineral. It forms by crystallization of magma, and it includes some uranium. Some of that uranium is uranium-238. Some of it is 235, depending on when this igneous rock formed after the beginning of the solar system. As soon as the mineral formed, the uranium is locked in the mineral, and it begins to radioactively decay. And because of the decay of uranium-235 is much faster than that of 238, right? It has a half-life that is about 7 times shorter than that of uranium-238. Its product will accumulate much more quickly in the mineral, right? We started out with nothing, and we end up with something. And because of this decay is much faster, we end up with more lead-207 than lead-206. Now, so we can measure the ratios of the daughter to parent isotopes, and they both start at 0 because, remember, we start with no lead. And given the half-lives of the radioactive parents, we can sketch out a curve that evolves in a predictable way as a function of how much time has passed. And you can see here, for example, that because the decay of uranium-235 is that much faster than uranium-238, we go up to values of lead-207 to uranium-235 that are almost 2 orders of magnitude larger than the ratio of lead-206 to uranium-238. And so a variety of rocks were measured on Earth, but more importantly, rocks that came from the moon. And then we, based on all of these measurements of the oldest rocks, we know that the age of the Earth is about 4.5 billion years. So we just heard that the age of the universe is 13.7 billion years. Over that period of time over which the universe has existed, there have been cycles of the formation and destruction of galaxies and stars. And about 4.5 billion years ago, stellar nebula, or the solar nebula, collapsed to form our solar system. And 4.5 billion years ago, essentially our sun and all of the planets and bodies that orbit it formed in the space of a few millions to tens of millions of years. All right, so now we have an answer about the age of the Earth. This long-standing debate of how old the Earth actually is has been settled because of the discovery of radioactivity. But as I mentioned before, the geologists who studied the sequence of sedimentary rocks realized much earlier, but without any quantitative estimates, that the sedimentary rock record represented very, very long time spans, hundreds of millions or even billions of years. And so without being able to constrain the absolute duration that was involved in generating these sedimentary rocks, they came up with principles that allowed them to determine relative timing. And these rules are the basics of stratigraphy, which is the description and study of the strata, the layers in the geologic record. And so the principles were formalized by a 17th century scientist who later became a priest, Nicholas Steno. And he stipulated the principle of superposition, which is to say that younger layers are deposited on older layers. The principle of original horizontality, which is to say that sedimentary layers deposit horizontally or on very shallowly sloping surfaces, and the principle of lateral continuity, which is to say that these units these layers are continuous over large areas. And just as an aside, these latter two principles let us infer things about tectonics, about structure, about movements in the earth, and about geomorphological processes, those that alter the surface of the earth, based on our observations of the effects of these processes on layers that were originally horizontal and continuous. But I don't want to go into that. The first principle, superposition, is what lets us, or what gave rise to the stratigraphic record. Stratigraphic record is a listing in order from the oldest to the youngest periods in Earth history. So we read it in this direction, starting at the beginning of the solar system, 4.5 billion years ago, and all the way to today. This is just one variation of it. There are some where you put all of these one after the other vertically. And what you can see is that it's split up into major and minor divisions. The largest of these, of which there are 4, are eons. The eons are the largest, the Precambrian, excuse me, the Hadean, the Archean, the Proterozoic, and the Phanerozoic. And you can see that the Phanerozoic is the most finely divided. It's hard to see the numbers over here. We're starting, of course, at 4.5 billion years ago and ending in today. But what's interesting is that there are many, many more subdivisions in the last 500 million years or so of Earth history than there are in the preceding 4 billion years of Earth history. So this little part here accounts for 88% of Earth history. This one, this here, the Phanerozoic, only 12. And so then what's the reason for this much finer division of the more recent units? Well, one reason is the survival of the rock record. The older a rock is, the less of a chance it has to survive and be observed today. So there may have been more sediments deposited, or there surely were more sediments deposited early in Earth history that have been eroded away or subducted because of plate tectonics. They've been driven back into Earth's mantle, and we don't see them anymore. But the more, the reason that they were able to more finely cut these more recent sediments into finer and finer time periods is because of the appearance of fossils, or the presence of fossils. So about 540 million years ago, the beginning of the Phanerozoic. Phanerozoic is the age of visible phanero life, or animal is zoon. Neither do I. I'm not exactly sure what these are. All right, so this is the age of visible life. This is when fossilized organisms began to appear in the sedimentary record. And this was originally thought to reflect the beginning of life itself. That 540 million years ago, it wasn't known at the time when exactly, but that time period represents the appearance of life on Earth. Now we now know that this is only the appearance of relatively abundant macroscopic life. That is life that can be seen with the naked eye. We know that microscopic life existed well before this, almost as soon as there were oceans about 4 billion years ago. So microbial life existed back to 3.8, maybe 4 billion years ago. The Phanerozoic is the appearance of macroscopic life, and we'll come back to that later in the talk. Now this was quantified by Jack SEPKOSKI, a paleontologist from the University of Chicago, And he compiled all of the reports from himself and others on the occurrence and characteristics of fossils to generate this Phanerozoic diversity curve. So we're seeing just the Phanerozoic, just the age of visible life, which is, again, divided into eras, the Paleozoic, Mesozoic, and Cenozoic. And what you can see is, and I don't want to go into the details here, is that diversity, which is the number of marine families as a function of time, really takes off at the Precambrian Phanerozoic boundary, the Precambrian-Cambrian boundary. You can see it take off here. We'll talk about some of the inflections here. And the reason that this lets us cut time more finely is because we can use the range of the occurrence of a specific fossil or an assemblage of fossils to define relative time zones. So here, for example, we have two organisms, this gastropod and then ammonite. And they each have a range of occurrence, right? This one evolved here or was first defined here and is lost from the record here, either because it became extinct or because it changed enough such that we would define it as a different species. This one appeared here and this appeared here. And between them, with the overlap between them, we can define three biozones. Biozone A, in which only this ammonite was present. Biozone C, in which only the gastropod was present. And biozone B, in which both of them were present. And so this is what we can do with just two fossils. If we have many different organisms and assemblages of fossils, we can really cut time quite finely. And this is the reason that the Phanerozoic is so finely cut. These 540 million years are so finely cut into relative time periods that we have been able also to pin to absolute time by radiometric dating in each of these rock sequences. And so what I'd like to do next is give a few examples of how the divisions in the stratigraphic record reflect observable changes in the rocks, which geologists noted a long time before they knew about absolute ages. And we'll examine the boundary between the Archean and the Proterozoic, the Archean here and the Proterozoic, where a major environmental change resulted in clear changes in the appearance and characteristics of sedimentary rocks. And then we'll look at the Precambrian Phanerozoic boundary, which we talked about now, where macroscopic life first appeared. And then we'll be in the Phanerozoic, where many of these subdivisions were defined on the basis of the disappearance of organisms, basically mass extinctions. And so we can see this in the SEPKOSKI curve as these downturns. And we'll have the largest of which we call the big five. These are the largest five mass extinctions, which took out a largest fraction of the species on the surface of the Earth. There's actually an ongoing debate whether we're in the midst of a sixth major mass extinction today, based on the rates of extinction of animals, which we are responsible for, of course. And out of these, we'll look at just the largest of these, which is the Permo-Triassic mass extinction that took out a large majority of life on Earth. And which also defines the boundary between the Paleozoic and the Mesozoic. Thank you. All right, so starting with the Archean-Proterozoic boundary, this is a story about iron, or more precisely about the oxidation state of iron. So now I've taken the geologic timescale and turned it on its side and put it all one on top of each other, starting in the Hadean, the Archean that I mentioned, the Proterozoic and the Phanerozoic. This is the part of Earth history where macroscopic life exists, as I mentioned. Now, this is the frequency of rocks that we are named banded iron formations. They're iron-rich and silica-rich sedimentary rocks. And this is what they look like in core. These are cylindrical cores that are drilled into the earth, and these rocks are pulled out. You can see they're green and gray, and this is because iron in them is ferrous. It's iron 2+. It's a relatively reduced form of iron. Now, because ferrous iron is relatively oxidized in the presence of oxygen, the accumulation of such large masses of iron is basically telling us that very little oxygen existed in the oceans. These are marine sedimentary rocks. They form in the ocean. And for so much ferrous iron to flux through the ocean can't have had much oxygen in it. Now, with a few notable exceptions, I won't go into, these rocks all but disappear about 2.5 billion years ago, the boundary between the Archean and the Proterozoic that I mentioned before. Iron begins to show up in ferric oxide cements in siliciclastic rocks. These are called red beds. So this is now an oxidized form of iron. The same happens on land. Iron begins to appear in oxides in soils, whereas before it was washed away from soils together with soluble elements like calcium and magnesium. And together this tells us that these changes in iron mineralogy and oxidation state reflect the rise of atmospheric oxygen. So something happened here, something happened here that led to a change in the cycling of this reduction oxidation sensitive element iron, such that it stopped appearing in its ferrous form in the geologic record and began appearing as rust in the geologic record. And what we understand that this is the rise of atmospheric oxygen. And now this is a curve as a function of time, the atmospheric pressure of oxygen, or the pressure of oxygen relative to today, where 1 is today, and this down here is a millionth of levels today, of oxygen levels today. And what we can see is that about 2.5 billion years ago, going from less than a ppm, less than a part per million oxygen in the atmosphere, we went to a few parts per thousand in the atmosphere. And this caused a major reorganization of all the cycles of any elements that could react with oxygen. Iron is one of them, carbon is another, sulfur is another. So what brought about this change? Microscopic photosynthetic bacteria. So basically around this time, cyanobacteria, which were the first photosynthesizing organisms, or the first ones to do oxygenic photosynthesis, they evolved and they began to split water in order to fix carbon dioxide to form their biomass. And in the process, they generated oxygen. And this accumulated in the surface ocean until it led to this change in the oxidation state of the oceans and atmosphere. And remember, we learned about this change originally without knowing any of the geochemistry and any of the isotopic evidence that now has led to the generation of this curve, simply by observations of changes in the properties of rocks, in the mineralogy, in the color, in changes in the sedimentary record. I'm running out of time, so I'll go through this, the Cambrian explosion quite quickly. This is the next transition that I'd like to discuss, which is the transition from the Proterozoic to the Phanerozoic, the appearance of macroscopic life. You've seen this before. This is when animal fossils began to appear in the geologic record, in the sedimentary record. But these examples are of very charismatic fossils that are not what we observe in this transition. In fact, when you look at this transition, the rocks don't appear to change much at all. This is where this man is pointing. This transition is in fact defined by the appearance of this trace fossil. This trace fossil is basically a burrow. This is a hole in the mud that a worm dug that was then infilled with material that was different, and so it was fossilized, or it was lithified, turned into stone, into rock quite differently. So, not very spectacular, right? But this first appearance marks the beginning of a very rapid diversification, which is sometimes called the Cambrian explosion, and which led over the course of only a few tens of millions of years to the evolution of all the major families of organisms in the animal kingdom, and this includes our earliest ancestors, the stem chordates. And the reason that this dramatic, this dramatic diversification is still being studied. We don't know if it's because of the onset of predator-prey arms race, if you will, or because of a change in nutrient regimes. But again, this is a major evolutionary event that's recorded in sedimentary rocks that we basically learned about by looking at sedimentary rocks even before we could time them. The last event that I'd like to mention is the largest mass extinction in Earth history, which is the Permo-Triassic mass extinction. Here we see the number of marine species, and whenever this gets truncated, this means that the species basically disappeared. And we can see that about 250 million years ago, many species, both in the ocean and on land, disappeared. About 90% of marine species, 75% of terrestrial species. These are just some examples of the species that went extinct on land. These are not dinosaurs. This is a human for scale. So They're scary looking, but quite small. And I won't go into any details about this, but this is because of major volcanic eruptions that emitted massive amounts of carbon dioxide into the atmosphere, because these massive, what are called flood basalts, the Siberian traps, you can see the US for scale here, they covered a huge area and they erupted through fissures, but they came up through major coal deposits. These are Russia's economic coal deposits. They came up through major coal deposits and emitted a lot of carbon dioxide. This carbon dioxide acidified the ocean. It causes many climatic effects that ultimately ended up causing the extinction. And just as an interesting aside, the Siberian traps are thought, based on various estimates, to have emitted between 5 and 50 gigatons of carbon per year. We are currently emitting about almost exactly 37 gigatons of carbon per year. So it's interesting to note that rates of carbon dioxide emissions similar to what we are putting in the atmosphere every year led to one of the biggest mass extinctions in Earth history. And so I'll leave you with my summary, only to say that we know the Earth is 4.5 billion years old. And before any such knowledge, the stratigraphic record told us about the major events in Earth history. And with this, I'll thank you for your attention and take questions.
Thank you very much. There may be time for just one very quick question.
כן? Mine. Okay, so the question is about where did water come from? So I talked about water. Where did water come from? Water, so the elements hydrogen and oxygen, or hydrogen and helium were generated during the Big Bang. Oxygen is then generated during nucleosynthesis in stars. Once these stars explode in supernovae, for example, and their material gets dispersed, ultimately that forms solar or stellar nebulas that end up collapsing to form additional stellar systems like our solar system. Once things cool down enough, things begin, once temperatures decrease enough, materials begin to condense. This starts with various oxides, ends up with various silicates, and then the volatile compounds condense once temperature is low enough, and water is one of them. That water is a part of any body in the solar system, depending on the distance from the sun, and where the temperature is low enough such that water condenses, which we call that the ice line. The Earth got its water either originally as it condensed from the solar nebula, or there are some ideas that the water came from comets. In any case, it came early, and we have evidence for large-scale water bodies, essentially an ocean, as early as about 4 billion years ago. There are sedimentary rocks that are about 4 billion years old that were deposited in large masses of water. So where exactly the water came from, whether it was primordial or, well, it's primordial in any case, whether it was a part of the original endowment of the Earth or whether it came in comets is still being debated. But in any case, it was present from very early on in Earth history.
Thank you very much, Itay.